For the n-Lorem Foundation, N of 1 doesn't mean alone because every patient matters. Hope for nano-rare patients and their families has never been more within reach. Visit n-Lorem.org today to donate and make hope possible. This episode of the n-Lorem Patient Empowerment Program podcast is proudly sponsored by Hanjin Biotech. With more than 26 years of experience in the nucleic acid industry, Hanjin is a specialized CDMO and raw material supplier committed to providing high-quality and high-value products and services with the best-in-class lead times.
Hello and welcome to the n-Lorem podcast series, a series that focuses exclusively on patients now referred to as having nano-rare mutations. I'm Stan Crook, and I'm the founder, chairman, and CEO of n-Lorem. n-Lorem is a nonprofit foundation that I initiated in January of 2020. Our mission at n-Lorem is to take advantage of the technology we created at Ionis Pharmaceuticals, Antisense technology, or ASO technology, to discover, develop, and provide experimental ASO treatments to nanorel patients, and to do that for free for life. Today, we'll continue our conversation about the various means that cells in your body use to communicate with each other. In the previous episode, we talked about the fact that each of us is a complex society of cells that form an organism that's several trillion times the size of any single cell. And that organism is formed from a society of cells. For the most part, throughout life, most of your cells behave according to societal rules, supporting your health and well-being. And very often, your cells sacrifice themselves for the greater good. And to do all that, they have to communicate constantly. And to communicate constantly, there are a variety of mechanisms that have been evolved. In the previous conversation, we focused on long-distance communication, in which cells in one organ can communicate with cells in another organ. Of course, the most rapid form of communication, long distance, is through the nervous system. And you have a central nervous system that manages the integration of all the signals you receive and the elaboration of signals that will drive you to various actions, and a peripheral nervous system, which then transmits signals to the central nervous system and from the central nervous system. You also have a nervous system called the autonomic nervous system, which regulates the essential functions of your body, like blood pressure, pulse, breathing, GI tract, and GU tract performance. And as is obvious, the nervous systems convert chemical signals into electrical signals. Then those electrical signals are propagated very rapidly to the nerve end, where they're once again converted from an electrical signal to a chemical signal that travels to the adjacent cell at the end of the nerve and transmits the information that's needed. So we can think of that circuit as a chemoelectric circuit. A second circuit that we discussed is strictly chemical. And the simpler chemical circuits are going to be slower communicating than through the nervous system. It's sort of like comparing a telegraph to the Pony Express. But you use both. And the chemical circuits are established in such a way that generally there's a hierarchy of organs and a master organ telling a slave organ what to do and how to do it. And those chemicals that we talk about forming chemical circuits are what we think of as hormones. Now, most hormones, as I mentioned last time, are secreted by organs that we think of as endocrine organs, like the pituitary, the adrenals, the testes, the ovaries, and the like, but not all. Some hormones are secreted by organs that have other functions, such as the liver and the kidney and organs like that. But irrespective of whether the hormone is elaborated by what we think of as an endocrine organ or an organ that we don't think typically of as an endocrine organ, the process is roughly the same. That is, a chemical is made, it's secreted by one organ, it travels by blood to a second organ, and then it orders that organ to do something. And so those are your long distance ways of communicating. there are other short-distance communication processes that play critical roles, and these communication processes are still less understood than the long-distance means of communication. So I expect that over time we'll identify other means of communication locally. One form of local communication between cells is called paracrine communication. And paracrine simply means nearby communication. So cells that are near one another can talk to each other locally. They don't have to go through the nervous system. They don't have to secrete hormones in blood, but they can talk to one another locally. And often, most of the time, paracrine communication occurs between cells in an organ. And to do that, chemicals are released from one cell into the extracellular fluid. That those chemicals traverse that extracellular fluid to interact with a nearby cell through an interaction with the targeting molecule that we think of as a receptor. These chemicals that are secreted have to cross that intercellular barrier and eventually interact with the right cell. And so you have secreting cells, and you have cells built to respond to those chemicals that are secreted, and the recipient cells then have receptors for those chemicals. And a receptor is nothing more than a protein that's typically a protein that's expressed on the cell surface designed to be affected by a particular chemical that is encountered by that cell. So the types of chemicals that we tend to think of as paracrine communicators tend to be pretty small. They tend to be pretty water-soluble and fat-soluble, so maybe amphipathic, or they may be interacting with ion channels and be ionic. But in any event, they are capable of moving from fat, the membrane of one cell, to water, the extracellular fluid, to the membrane of the next cell. So, key point, cells near one another can communicate over short distances, and this form of communication is called paracrine communication. Paracrine communication involves the establishment of a chemical network. That is, a chemical that is secreted by one cell, traverses the extracellular space, and interacts with the recipient cell that has the right receptor on its cell surface to interact with that chemical. And so it is a communication between neighboring cells that is purely chemical in characteristic. You've got cells talking to one another through the nervous system and with hormones at great distance, and now you've got some cells next to each other talking. What about if you want to talk to a cell near you and provide more complex instructions? And more complex instructions mean more complex chemicals. And generally, the more complex chemicals are polymers like proteins and RNA and DNA. So there isn't a form of communication that's been identified by which cells can release large molecules that contain a lot more information and interact with recipient cells. And the way you do that, because the large molecules are big, is they tend to be secreted by the communicating cell in little fat droplets. And those fat droplets are called exosomes. And so exosomes form when little bits of cell membranes, the plasma membranes, break off and they're released. And since the exosomes derive from the membranes and are fat soluble, and as they form, they enclose the nearby cytoplasm. This means that they can include a good many molecules, and those molecules can be quite large. These exosomes look like a little bit of membrane surrounding what would be cytoplasm. And they can float in water because they're like little soap bubbles. Those, when they reach the target cell, because they are little bits of membrane, they can basically fuse with the membrane of the target cell. And in so doing, they dump the contents of that exosome into the recipient cell. So it is a well-orchestrated process that is capable of delivering large amounts of information in large molecules across a small distance, and it depends on the formation of exosomes by a donor cell and the receipt of exosome by a recipient cell. So it is another means of communication at the short range distances that supports the effective distribution of large amounts of information, not the kind of information that can be carried in a small molecule. It also may be the way some viruses spread from cell to cell because they've adapted so they can take advantage of these exosomes. A second shortwave communication is through exosomes. Exosomes are recently discovered means of packaging and large amounts of information and communicating between cells that are near one another. They involve the formation of little soap bubbles of membrane plus cytoplasm that can cross the extracellular space, fuse with the membrane of the recipient cell, and release the information into the inside of that cell. So that's exosomic communication. And I should say this is all new stuff. Exosomes were only discovered maybe 10 or 15 years ago, and we're still learning a lot about them. The key point about exosomes is because they can include many different molecules and large polymers, they can transmit a great deal more information to recipient cells than could be done with a simple little chemical that might be secreted by a recipient cell. And in that level of information that's being transmitted, you can have very fundamental processes change in the recipient cell. Okay. There is a final way that cells can communicate, and that's called Juxtacrine. That's just another fancy word that means that in this kind of communication, cells must touch each other. And in the fact that they touch one another, that opens up opportunities to communicate. Now, you know that most of the cells in your body are negatively charged at the surface. So there's a natural repulsion between cells. So any time that two cells are going to touch, there has to be something that's driving those cells to actually overcome the strong electrostatic repulsion that's caused by the fact that the outside of the membranes of both those cells are negative. And indeed, there are things that drive that. And as you might expect, what drives it is proteins expressed on the surfaces of individual cells that attract one another. Many of these proteins are called cell adhesion molecules. It's a pretty good name when you think about it. They are proteins that encourage cells to adhere to one another. Originally, it was a fairly narrow group of proteins, but the number of proteins that seem to be capable of bringing two cells together to fuse for a bit is growing. And the more we know, the more versatile the Juxtacrine approach to communication is. But certainly, the cell adhesion molecules were the first to be discovered. So if you have two cells that actually fuse their membranes, actually become, in effect, one continuous cytoplasm, you can imagine trading incredible amounts of information. Anything that's in the cytoplasm, you could transmit a virus, you could transmit a toxic particle, you could transmit a mitochondria, subcellular organelles of all sorts. And so it's very much the case that juxtacommunication is the most elaborate means of local communication that we know of today, in that the two cells are sharing for a short time their cytoplasm, and they are trading all the information that's contained on the inside of those cells back and forth. And so in juxtacommunication, both cells can be affected by the material that is transferred, because the transfer goes both directions. So, key point, since most cells are negatively charged at the cell surface, they tend to repel each other. And to overcome that electrostatic repulsion, we have special proteins and lipids that are designed to overcome that barrier and connect two cells together. And when they do, in effect, those cells are sharing their cytoplasm, and so they can trade incredible amounts of information. This process is just beginning to be really understood. And as you know, cells can move. And they do that like an amoeba, if you've ever looked at an amoeba under a microscope, jutting out little bits of plasma membrane and cytoplasm, and those are called pseudopodia, that is fake feet, and then dragging the rest of the cell behind it. And in fact, the term that is used is philopodia, meaning little feet. And so as cells move, the philopodia drive the motion in a certain direction. And it's the philopodia typically that first interact with the philopodia of another cell. And if there's a match between the proteins on the surface of the two cells, then they can fuse at that site, and that fused membrane then will get larger over time. And in the meantime, a ton of information is transferred between the two cells. There's a term for the connection between the two cells, and they're called tunneling microtubes because they're comprised of the structural elements of cells that give cells shape, which are microtubules. And basically, it's just a little tunnel through which big stuff can go through. These structures are transient, but can transmit an incredible amount of information that can have profound effects on both cell types. So key point Juxtacrine signaling is usually established by protrusions of the cell membrane that allow the membranes of two cells to fuse in a local area, and then that fused membrane can expand over time. And the information that's transmitted is transmitted through a structure that you can actually see on a microscope that's called a tunneling microtubule. So the point is that cells in the same organ must cooperate with one another and often must share large amounts of information. And by forming organs, cells that need to cooperate constantly are close enough to each other to share large amounts of information, either through paracrine means, exosomic means, or by actually fusing together and sharing their cytoplasm. So there is a solid reason why you have organs. And you have organs to facilitate local communication of large amounts of information. And you can imagine then, if you were a virus and you wanted to infect a bunch of different cells, you would adapt. Maybe I get into one cell, and then I participate in this cell fusion, and I can infect the next group of cells and the next group of cells. And that is what happens with viruses. And it may be one of the ways that prion disease, for example, which is not a virus, but just a protein that are a bunch of aggregates, form and are transmitted from one neuron to the next. So to bring this conversation about conversation to a close, once again, we are societies of cells. And we are a society that's 3 trillion at least times larger than any single cell. In order to form a society, you must communicate between each other. And our cells communicate constantly, both long distance and short distance, using a variety of means, both electrochemical and chemical. And our long distance communication, because it needs to be fast, is managed through a chemoelectric circuit that we call the nervous system. Long distance communication that can be slower, the Pony Express style, can be managed through the secretion of chemicals into the blood and letting those chemicals take the time it needs to go from one organ to the next in the blood to then effect the change that they want in a target organ. Within an organ, there are short-range communications called Paracrine Communication, exosomic communication, and Juxtacrine Communication. That is when two cells have to touch. So it is an incredibly robust, multifaceted process to assure good societal communication. Goes on all the time during your life. So with that, I think we've dealt with all we need to with cell communication, why you have organs, and all of the various means that your cells use to talk to one another to make you who you are and keep you healthy, wealthy, and wise. Well, at least make you who you are. Hopefully you're healthy, wealthy, and wise.
n-Lorem is a nonprofit committed to discovering and providing personalized experimental treatments for free, for life, to patients with genetic diseases that affect 1 to 30 patients worldwide, referred to by n-Lorem as nano-rare. Many of these patients progress and die without ever achieving a diagnosis. This is where n-Lorem comes in. They do the impossible by providing hope, and for those that they can help, free lifetime treatment. For more information about n-Lorem or today's episode, visit n-Lorem.org. Any questions can be sent into podcast@n-Lorem.org. Search n-Lorem on Twitter, Instagram, YouTube, LinkedIn, and Facebook to connect with us. Please rate and review the podcast on Apple, Spotify, or wherever you listen. This truly helps us climb the charts and allows others to find the show. This podcast is hosted by Dr. Stan Crook. Our videographer is John Magnuson of Mighty One Productions. Our producers are John Magnuson and Kira Deneen of DNA Today. Thank you for listening.